So I'm Aaron, a PhD student from the TU Darmstadt, and the title of the presentation is Quality Factor Statistics of a Coded Superconducting Radio Frequency Cavity. Now there's maybe some words here that you're unfamiliar with, so I'll give a brief introduction and also a motivation, of course, of what exactly we're trying to study. Tell you something about the numerical methods we use in order to solve it, and finally, of course, the results of the study. So first of all, what do I mean with cavity? What do I mean with quality factor? So essentially, a cavity is an electromagnetic resonating structure. You send in an electromagnetic wave of a specific frequency. It excites an eigenmode that you want to use for some application. The one we have in mind here is particle acceleration. So we have a particle bunch that goes into this structure that has an electric field inside that causes the acceleration. The geometry that you see here is called a Tesla cavity and is used in, for instance, the European XFEL in Hamburg, Germany. Now, the quality factor is a measure for how well the fields are maintained within the structure over time. As I showed there, the energy inside decays exponentially with the reciprocal of the quality factor. So higher quality factor means the fields maintain inside the structure longer. And for reference, I show values for copper and niobium there at a temperature of 2 Kelvin, and you see multiple orders of magnitude difference, which comes from the fact that niobium is superconducting while copper remains normal conducting at this temperature. So perhaps unsurprising, this niobium is a material that you currently use for this application, but they are reaching, very advanced surface preparation techniques have caused these things to reach like the theoretical limits of what you can do with niobium. So they are looking at alternative materials you can use there. And one of the observations is that the benefits of having a superconducting material happen within a very thin layer, about a micron of thickness. And materials with better properties, so higher critical temperature, higher critical magnetic fields, this type of stuff, are typically brittle materials that you cannot manufacture in a bulk shape like this in the first place. So the idea is to add a very thin layer on top of an existing substrate with these better materials, so you get these nicer properties. For instance, you can shield the interior from magnetic fields, so you can have higher fields inside. The thin layer shields the bulk material, and you maintain your superconducting state at a higher field inside your structure. And of course, also you can increase potentially the operating temperature, which would cut cryogenic costs by quite a lot. Now, in order to get a thin layer on there, you need some deposition method, and this is inherently going to cause some inhomogeneity. So the thickness of this thin layer is going to be different depending on where you are in your cavity. So the question we were trying to answer is, can we numerically determine what the effect of this inhomogeneity will be on a quantity of interest, such as the quality factor? Now, for the numerical methods, of course, you have the electromagnetic eigenvalue problem. So this is the problem that gives you the field I showed in the beginning, and at what frequency this field is excited, and the quality factor for this particular eigenmode. Now, since we have a quality factor, means there's losses involved somehow, so you cannot just have a Peck boundary condition. You need to have a surface impedance boundary condition. Let's see, does this pointer do things? Yes. So this surface impedance here contains basically all the information of this multi-layer structure. So all material parameters, thicknesses, everything is in there. I will not go into any further details, but all of it's included in there. And of course, you see it depends on where you are on the boundary, because it depends on the thickness of the superconducting thin layer. Then, of course, you go through the motions and to get to your weak formulation, which is in this case a nonlinear complex valued eigenvalue problem, where the nonlinearities are located in this term mostly, so only on the boundary and involving this surface impedance. Then the second question is, how do you get this thickness distribution for the thin layer? Where do you get this from? So ideally, you would like to have some experimental data that tells you what this looks like. Unfortunately, it does not exist for the moment. So we used a Gaussian random field instead. So examples of this are shown here on the side. And they depend on a length scale, which basically tells you the length scale over which the deviations occur. So if you have a higher length scale, the deviations occur over a larger length scale than they do if you have a smaller length scale. So the thickness of the superconducting thin layer is expanded into some global average, and the deviation from that average that is sampled as a Gaussian random field. Now, how you get this practically is you solve a stochastic partial differential equation on the boundary. Yes, so solving this equation, you get as the solution this deviation from the global average, and of course you can again use finite elements to get there. So all in all, how does it all fit together? You have a mesh and a boundary mesh, and you have maps in between them with these entity maps, which FEniCS introduces, which is very useful for this application. On the boundary, you solve a finite element problem that gives you the thickness of this superconducting thin layer. This goes into a surface impedance model that is involved in the boundary condition of your eigenvalue problem. Solving the eigenvalue problem gives you the quality factor, and you repeat and sample multiple of these fields on the boundary. Particularly, we took 8 different length scales for the random fields, 2048 samples for each of the fields, and specific materials, specific thicknesses. So what do we find? So first of all, here is a box plot of the results, which is rescaled to the quality factor you get from a uniform distribution at a specific thickness, namely the global average we are looking around. When you look at the distribution of the quality factor, they are normal in each case, so it's very nice to work with. First observation is as you increase the length scale of your Gaussian random fields, the spread of your quality factor increases, and if you look at extreme observations, you get a 2 to 6% difference from the uniform value. Of course, since things are normally distributed, you can talk about means and standard deviations. Here I show a plot of the mean and the standard deviation where the error bars are the confidence intervals, 95% confidence intervals of these quantities. And then you can perform a series of statistical tests to see, can I see any differences between these different length scales in the Gaussian random field. So if you compare the standard deviations, you find that they can be differentiated at each length scale and that they are increasing with the length scale. If you compare the means, you find that most of them can't be distinguished, only the one at 4% here and the one at 20, 24, and 28% can be distinguished, but the p-value is like slightly below 0.05, so it's not very, very significant. What you also see is that, so you have here the one on top, which is of course the uniform value. This lies significantly outside of the error bars of the mean, so just having this inhomogeneity already decreases your quality factor by an amount that we can see here. Okay, so what I have shown you is a simulation scheme essentially for how you can determine the effects of these inhomogeneities in your deposition method on the quality factor of a superconducting cavity. We saw that the standard deviation of your quality factor increases at the length scale of your deposition deviations. And we saw that we cannot distinguish the means of these distributions that well, and furthermore, we have the extreme observations, which I think is most interesting for the manufacturing people. If you're manufacturing thousands of these cavities, you want to have an idea of what you can expect in extreme cases. So depending on what length scales, you can get 2 to 6% from what you would expect from just uniform. So thank you very much for listening, and we can move on to questions.
Great, thank you very much. Questions from the audience?
Yeah. Thank you very much for your presentation. I have a question, 2 questions, short ones. So you sample your Gaussian field by solving a PDE on a manifold, right?
Yes.
And do you use multi-parallel or other techniques to speed up the convergence?
No, so it's just random sampling. Yes. So.
How do you justify that you have enough samples for the Q factor for extreme observations?
The thing is that it's just basically limited with how much time you have to simulate these things. So this took quite some time, and I think it was 2 months of simulation time.
Just one sample?
No, not one sample. That would not work, right? Just the entire thing, but you kind of, I mean, it's numerics, right? So at some point you need to stop how many samples you take, because you could take infinitely many if you had infinite time. But it was basically let's put a time budget of this much and see how far we get that way. Yeah.
Thanks.
Yep.
Do you plan to calibrate the random model of the manufacturing defect on any data?
Yeah, if once it exists, yes, then I would be nice indeed to, because now you're just doing like, okay, let's say Gaussian random fields, and we say nothing about maybe there's some rotational symmetry or whatever. Like there's, for instance, DC magnetron sputtering is called, where they put a thing inside and rotate the cavity around it. So maybe there you would expect this thing to be much more rotationally symmetric, the coating distribution, and in this case you would, then of course want to reject certain samples you're making, but until I know more, it's difficult to say. Yep.
Thank you very much. Sometimes these thin coatings, they fail because of thermal cycling or
Yes.
fatigue
Yes.
I know it's probably a very different type of model to predict this failure, but do you have ideas of how to account for that? Maybe a failure rate or something like this, because this will have an effect on your.
Yes, but I think if it fails, then your cavity just breaks. It just melts, or if it's in.
It might not fail everywhere. It might fail locally.
Yes. Gonna have a quench somewhere. That's a different simulation.
It's
So,
maybe a contamination problem.
yeah, I suppose so. Yeah.
It's hard to simulate that, I guess.
Well, there's people that do quench simulations, so I guess there's people that could study that instead. Yeah.
More questions? Yeah, maybe. I didn't really get into the modeling that you were doing, but could you say something about uncertainties? Is it computational uncertainties, like mesh convergence, or is it?
No, it's just so you sample something on the boundary.
Mm-hmm.
This is random,
Mm-hmm.
so then you get a quality factor out, and then you repeat this process, so you get some kind of distribution for the quality factor.
Mm-hmm.
This turned out to be normal, and then you can, of course, give this normal distribution has a mean, has a standard deviation, and an confidence interval for what that mean and standard deviation are. So it just comes from statistics, nothing.
Yeah. Okay. So but you said something interesting, that it was expensive to compute or something. Could you say what is expensive?
The problem was that I did it on my laptop instead of doing it on an HPC system, because I was too lazy to put it on there.
You can just do all the samples in parallel.
Yes. So
Be done in a day.
stupid me did this on my laptop and just let it run. So perhaps in the future I can change this. But
maybe I can just propose. So what we're doing for aerospace typically as a showcase. So these like publicly available resources like Google Colab. I'm not pushing Google. You can almost any resource. Then you can just connect in a Jupyter notebook and a web browser. You get a virtual machine, and I think it costs like $10 per month for 40 cores. Then maybe you have 40 times speed up.
Well, I have access to an HPC system. I just have not used it.
Yeah. But I'm just saying, usually then maybe you need access and you need to install stuff there.
Yes.
But here you do it it's just your root on a virtual machine. It looks exactly like your laptop, and you do it in the web browser, so you don't need to send like a passport to be approved to the HPC admin. Yeah, just a proposal. But maybe let's move to the next speaker. Thank you very much.
Yes.
Thank you.